So, good evening, everyone. We are delighted to welcome you to tonight's lecture, which is part of our ongoing Frontiers in Science lecture series. With this series, we aim to bring the latest developments in international cutting-edge research to a broad, multidisciplinary audience within our university community. Each semester, we invite a renowned researcher to share their work and discuss its implications for the pressing challenges of the 21st century in science, politics, and society. Together, we explore the leading questions, theories, and methods that push the boundaries of scientific discoveries. Tonight, we are honored to host Professor Élisabeth Guazzelli, an internationally recognized expert in fluid mechanics, who will deliver a lecture entitled Unraveling the Nature of Granular Suspension Flow. Granular suspensions, complex mixtures of particles and fluids, are everywhere around us, from industrial applications like concrete production and waste management to natural phenomena such as sediment transport and lava flows. In her lecture, Élisabeth Guazzelli will guide us through the fundamental principles of suspension rheology, shedding light on fascinating phenomena like shear-induced migration and shear thickening and their applications in both science and industry. We only just see the relevance of this topic in Switzerland, where a whole village has only recently been buried. Élisabeth Guazzelli has had an extraordinary career. She received her academic training at the École Normale Supérieure de Fontenay-aux-Roses, the University of Paris Sud, and the University of Aix-Marseille. Over the years, she has led research groups at the IUSTI laboratory in Aix-Marseille and now at the MSc laboratory of the University of Paris Cité. Her contributions to the field of fluid mechanics have been widely recognized. Among her many accolades are the Euromed Fluid Mechanics Prize in 2016, the American Physical Society Fluid Dynamic Prize in 2023, and last but not least, the Gay-Lussac Humboldt Prize in 2024. She is also a fellow of the American Physical Society and the European Mechanics Society and a member of the US National Academy of Engineering. Beyond her research, Élisabeth Guazzelli has played a vital role in the academic community, serving as an editor for leading journals such as the Journal of Fluid Mechanics and the Annual Review of Fluid Mechanics. In her own words, Élisabeth Guazzelli's scientific approach is driven by asking the right fundamental questions using frugal experimental methods and challenging accepted theories. Her work not only advances our understanding of fluid mechanics, but also holds the potential to address real-world challenges such as mitigating the risks of geophysical flows like mudslides and debris flows in a changing environment. Currently, she is at our university as part of the Gay-Lussac Humboldt Prize, which will facilitate an enhanced research collaboration between her and scientists at TU Dresden, particularly with the group around Professor Bernhard Vohwinkel, who holds the chair for transport processes in hydrosystems at TU Dresden. Before we begin, I would like to hand over to him. Professor Vohwinkel will provide an introduction to Élisabeth Guazzelli's field of research and its relevance to our university. Dear Professor Guazzelli, we are thrilled to have you with us this evening and look forward to your insights. And dear audience, thank you and enjoy the lecture. And with that, I hand over to Professor Vohwinkel.
Thank you. Dear Rector, Professor Staudinger, dear Vice Rector, Professor Rosenwolf, dear colleagues, dear students and guests. It is also my pleasure to introduce to you tonight's speaker, Élisabeth Guazzelli from the University Paris Sud. While we know much about her great academic achievements, I want to start on a bit more of a personal level, which is how we met. So Élisabeth, or Babette, and I, we met at a workshop on dense suspensions at the Cavalier Institute for Theoretical Physics in Santa Barbara in 2018. And at that time, Babette was a distinguished speaker, and I was a postdoc in the group of Eckhard Meyerburg at UCSB at the time. And I was doing research on simulations of geophysical flows. And so I also attended this program, and during this time, it happened that a very strong mud flow hit the neighboring town of Montecito. And this mud flow was actually triggered by a short but intense rainfall that followed a big wildfire. Now, this is actually called a compound event. So you have a drought and then a wildfire and then the rains that trigger the mudslides. And this is exactly the core of the research that we do in the Faculty of Environmental Research and Environmental Science. So, of course, this event raised immediate interest and attention in the participants of the KITP program in Santa Barbara, because those mud flows are, by definition, violent torrents of dense suspensions, and they even have the capacity to mobilize boulders, and their dynamics are, of course, very complex and far from being fully understood. And owing to their dynamics, they can cause huge destruction in urban infrastructure. Unfortunately, that was indeed the case in this tragic event of Montecito, where 23 people died and more than 200 million US dollars of damage were caused. So it was under these circumstances that Babette and I connected, because it was immediately clear that there was a very nice overlap in our research interest. She, of course, was very well known to me because she has made important contributions to particulate multiphase flow and sediment transport processes by combining experimental and modeling techniques with intuitive physical insight. This aligns very well with the focus of my research group, where we conduct highly resolved numerical simulations of sediment transport processes. And since then, we successfully applied for, in 2022, for a joint German Research Foundation, ANR, French Research Foundation project to investigate the rheology of sediment beds. This fruitful collaboration has already resulted in 4 manuscripts, one already published in JFM, one as a book chapter, one submitted to physical review letters, and one in preparation. And of course, the recognition by the Gay-Lussac-Humboldt Research Prize for German-French collaboration. And this is currently further strengthening our collaboration by having Babette visiting us for extended periods of time. In the meantime, lessons learned from the unbroken and increasing momentum of climate change have taught us that there is indeed a need for research on mud flow dynamics, and it's more urgent than ever. We see increasing frequency and magnitudes of these catastrophic events where the interplay of water and sediments play a key role. And like Professor Rosenwolf has just highlighted, the latest example from Switzerland was in the news last week, where a glacier collapsed in the aftermath of the thawing of the permafrost that then caused a huge landslide that buried the town of Blatten. So here's why I think our research can be useful to better understand sediment processes. So far, the onset of sediment transport has been described by a framework that is almost 90 years old, which is the ratio of a mobilizing shear force of the fluid to the resisting forces of the sediment grains, which is their weight. And this ratio is known as the Shields parameter. Since sediment beds, however, are very heterogeneous, such an approach is very prone to large errors. And what's even more important, sediment transport has been described as the excess shear stress with respect to its critical Shields parameter, and such an approach treats the sediment beds as if they were a non-permeable surface. And we all know, everyone who has stand next to a river knows that this is not true. They're actually a porous medium made out of grains that can be deformed under shear, and they can be flow through and around the grains. And so this is where the framework of rheology comes into place, where we learn more about it today. This rheological framework was developed by Babette and her co-workers for the last 15 years, and it now allows us to treat sediment beds as dense flowable suspensions that deform under external shear. A key property is that the microscopic friction, as well as the porosity of the porous medium, change with increasing shear, which is a surrogate for different flow rates. And then the macroscopic friction, as the anisotropy of the stresses in shearing and normal direction increases, while the porosity decreases. So for us in environmental engineering, this opens up the perspective to model sediment suspension as two continua that can be described by their momentum balances. A key property in such a framework is the stress exchange between the fluid and the particle phase, and Babette and I are now working on a more comprehensive framework to develop a flow description across a variety of flow regimes. And that's by covering viscously dominated as well as inertially dominated flow conditions, as we will see today. So such a framework and the fruits of our work, they have the potential to revolutionize this 90-year-old framework of shields. And because it can model the sediment transport in the environment more accurately with more predictive power and on scales that are then feasible for engineering-type practices, so that we can learn from the experiments conducted by Babette and the simulations conducted in my group how the stress exchange and the grain dynamics behave. Suffice to say that rheology of dense suspensions is not only limited to environmental and geophysical applications, it is also useful for processes in fluid mechanics, dealing with mechanical engineering, polymer research and chemical engineering, and additive manufacturing and civil engineering, where you have to deal with the flow properties of cement. I'm therefore very pleased to see this many people in the audience that do share our passion for particle behaviors in viscous flows. So in her talk today, Babette will take us on a fascinating tour covering many aspects of dense suspensions flows, relevant to a broad range of examples, and I'm very much looking forward to your talk, Babette. Please, the floor is yours.
Well, I want to thank all of you and both of you for these very kind words. I am very pleased to be in Dresden, and I'm very honored to have received the Gay-Lussac Humble Prize, and this gives me the opportunity to be here for a long period. And so we're working all together, and I hope at the end we won't have solved everything. But hopefully we will improve a little bit the understanding of the suspension flow. And okay, so today I will give you a little view of what is suspension rheology, suspension flow. This is a little bit, but I think Bernard and you have already introduced what I will be doing. I will try not to give too many equations because I was afraid that people will get lost, and I've tried to put movies because rheology usually is a field which seems very boring because you put stuff in a rheometer and then you have graph. But I think if you have movies, it's a little bit more appealing, I will say. So I will first introduce a little bit what is the suspension dynamic, because it's a field which has some time. It has started probably at the beginning of the 20th century, even at the end of the 19th century, with Stokes, the middle of the 19th century. But we already said that suspension refer to particle dispersed in a liquid of a gas. And as you have mentioned, you can find them everywhere, okay? In industry, and I give a few examples, but I will show you some movies later on concrete, which is fun. So I don't know, is it working? Yeah, okay. So here, you wonder what it is. Actually, it's paper. It's pulp and paper is made of fiber out of wood, and it's really a suspension when you process it, before processing it. And then you have ink and paint, which are made of fluid with little particles. Okay, and then this is something we talk a lot about. It's mud, and here it's a drilling mud, because when you do oil drilling, it's a bad thing, of course. We don't want to drill too much, especially in Europe. We don't have much oil. And anyway, when you drill, actually, to drill, you need to carry the particle, the soil which is inside. So you need to have a special mud sometime, which is used to do that. This is the sort of thing that you have here. We have also natural media, and of course we discuss again mud. This is a mud lake. This is sandstorm, and this is something which is kind of very important to model. This is, as you can see, this is something which is highly turbulent in sandstorm, but you have things which are much more laminar, like this is sediment transport in a river, like that, which is a little, but this is something which is very important also. And of course you have rain, and rain, it's a little droplet, and you can think about it as a suspension. So we can, and it's important to understand that. We have them also in living media. We all carry in our body some suspension, and this is blood. Blood is composed of this, in particular, this red blood cell, which are biconcave disc, and the size is about 9 micron, basically, and they are deformable, which is good for us, because when we run, they deform, so, and they are shear thinning. It's a shear thinning suspension, meaning that the viscosity decreases when you shear it, which is good, otherwise we will die when we run or we do some exercise. Okay, and then I have shown you other, this is bacteria, and there is million of bacteria in our body, and this is also suspension. This is what people call active suspension. This is sea urchin spermatozoid, which is also a suspension. So we have suspension, as I said, everywhere, and we really want to understand this. And I just gave some definition here. So what I said at the beginning is that suspension is a mixture where you have particles which are dispersed in a bulk of a thread, but there is also different names which are here. I won't go over all of them, but when we talk about sandstorm, we talk about aerosol because it's in a gas. It's a suspension in a gas, for instance, something like that. Okay, the order of magnitude, and this is interesting. I hope you can see it. On the top here, you have the diameter of the particle, okay? And you have the different type of particle that we can think about. And here, so you have, for a small particle, you have smog, you have colloidal silica, carbon black, and of course, we have viruses or bacteria. For large particles, we have dust, spray, sand, pulverized core. And here, we have the red blood cell, which are, I mentioned before, which are about 9 micron, okay? And I have different horizontal line here. One is the Reynolds number. Here it's diffusivity, and here it's the Pickley number. So I will discuss that a little bit. And this graph is coming from a paper of Batchelor, and I will mention who is Batchelor a little bit later. I'll show you a picture of him. So the Pickley number, so what is it? I said I won't show too many equations. The Pickley number is the ratio of the convective effect when you carry the particle divided by the diffusivity, which is the Brownian diffusivity, where the particles are moving like that, okay? So if you have a Pickley number, which is very small, that means that the Brownian motion is very large. While if you have a Pickley number, which is very large, the Brownian motion is inefficient, okay? So that's interesting. If I give you the limit, and basically it's 1 micron, because if you have 1 micron here, you can see that the Peclet number here is very large, above 10 to the power 4. Or even here, for 100 micron, it's 10 to the power 8, meaning that Brownian motion has no effect. Okay? This is more that I'm going to be interested in. Now, there is another number, which is the Reynolds number. Now, it's the effect of convection divided by the effect of viscosity. Okay? So if the Reynolds number is very small, we are in the case of viscous flow. So viscosity is dominant. We don't have any inertia. While on the opposite, when the Reynolds is larger than 1, inertia dominates. Okay? And if in this graph, when I show here, you have the Reynolds number here. So for 1 micron, the Reynolds number is 0.5, you can see. So above, it's increasing, you know, it's power 10 to the power 2, 10 to the power 4, but when you are below 1 micron, basically you have Brownian motion, and the Reynolds number is extremely small, while if you are above 1 micron, you may have inertial effect. We will discuss that. Okay. So now, if we want to understand the flow of the system, and especially what we were interested in is really when it's dense, we want to understand the rheology. And I will talk a little bit about rheology. And I want to show you 2 more examples, because they are the 2 examples which are a little bit the example we are really interested. One is here. It's self-compacting concrete. Concrete is one of the building material which is the most common on Earth. Okay, and it's made of grain of different size, especially for the self-compacting concrete. You have a lot of very small grain, and there is a binding fluid. So it says, and we want to understand the flow of that, because when they pour concrete somewhere, they want to understand how it's spread. Okay, this is an interesting engineering problem. Concrete by itself is not very good for the planet, as you know, because but anyway. Now, the second example, which is more in nature, is this river of rocks, which happened after this cyclone. And you can see that this is really impressive, because we have these huge rocks which are carried by this river. And you already mentioned the mud flow, even the lava. The lava flow, it's also something where you have suspension is important, because in lava itself, it's a Newtonian fluid, but you have because it changed with time. You have crystallite because it's solidified with time, so you have particle inside, and you have also bubble. So it's a very complex material. But here in this thing, you have rocks, and you can have mud flow. You can have these avalanches, what we call avalanches, debris flow. And this is really what we want to understand. And actually, 2 years ago, we organized a program in the Cavity Institute, and Bernard was here, and it was really multi-phase flow applied to geophysics. And really, we had people from different disciplines trying to work together to understand that. Okay? So now, of course, I'm not a geophysicist, and I'm trying to model things in a very simple way, in a very, as I say, frugal way. And what we do is we have model suspension. So we have little spheres, you can see here, which are carried, and we want to understand how they flow. This is an experiment which was done in Marseille with Pascal Ossius, and actually I will show that again, but just to tell you how we do that, we have PMM sphere, and we put them in a fluid which is the same index of refraction, and then we put a laser beam, and since you are the same index of refraction, you can see through. But we dye the fluid, and we put a laser sheet, and then that's why you can see the particle in black, and the fluid is behind, and it's a little bit bright. And we can cut into it, because the problem with this system is that you cannot see through, of course. And that's a way to see through. And in addition, here, we put some little particles which are, that you can see here, and which are telling us how the fluid flow. Okay? So, of course, this is model suspension. Then we want to understand the rheology of this model fluid, and we want to move toward more complex mixture of particle and fluid. Okay, and I like to start with this quote of Bachelor. George Bachelor was professor in Cambridge, at the Department of Applied Mathematics and Theoretical Physics, and he was the founder of the Journal of Fluid Mechanics. He worked on turbulence at the beginning of his career, and in 1962 there was a meeting in Marseille. Everything is in Marseille is a little bit weird sometimes, and there was Kolmogorov, who was here, a great name of the turbulence, and he had a theory, and this theory, the 1942 theory, was found to not work perfectly. So that was a big disaster for all the people working on turbulence. At that time, Bachelor changed subject and started to work on suspension and multi-phase flow. And if you think about multi-phase flow, it's a complex problem because it's two-phase system, of course, but at the same time, it's far from equilibrium because you have particles which are large. He was interested in particles which are non-Brownian. So we don't have a system which relaxes to a certain structure which is given by the Brownian motion. We don't know what it is. It's influenced both by the flow and by the structure of the suspension. So what he was saying is, in this seminal paper, what he wrote here is that he said that the mechanics of suspension is an especially important place in current study of rheology, in that we have the unusual opportunity of obtaining definite and explicable constitutive relation. I think it's not yet completely here. So maybe he was a little bit overstating things. Anyway, so that's the picture of Bachelor in Cambridge that we can see in the Department of Applied Mathematics and Theoretical Physics. So I want first to say the different regime of suspension, and here you have an arrow with the time, and this coincides basically with the understanding of suspension of different concentration. So you see that we started with very dilute system, and in the beginning of the 20th century, and we moved to more complex system. So the arrow coincides with the progress of understanding more concentrated suspension. And the first work on the suspension was done by Einstein in 1906 and 1911. I will explain why we have two dates. And he computed the viscosity of the suspension and explained that actually if you add particle to a fluid, the dissipation will increase, and therefore, if phi is the volume fraction, you have the first correction in volume fraction of the viscosity of the suspension, which is going like 1 plus, in that case, it's 2.5 phi. Okay? So, and why it's that? It's because if you put one particle in a shear flow, you shear like that. Okay? A shear flow can be decomposed into a rotation, which is here, and an elongation. So the particle rotates with the rotation, but because it's solid, it cannot deform completely with the elongation. So therefore, that's why there is this dissipation, because it's really the resistance of the rigid particle to the straining motion. And it's the same thing even for a red blood cell, because a red blood cell is a little bit deformable, but not completely. So it will dissipate more, okay? So now I have the picture of Einstein. Everybody knows him. But now I wanted to show you that, and because there is 2 dates, and a little bit of history of science, sort of. There's the first paper, which is 1906, and actually Einstein, his calculation gave 1 plus phi. And then there is a corrigendum, and you can read what, this is the introduction of the paper. And actually, he said that this guy named Basselin, who was working with Jean Perrin in Paris, did some measurement of the viscosity and found out that it was not working. He had something much bigger. So Einstein asked, I guess, a colleague of him, Prof, I don't know who he was, to redo the calculation, and they found this coefficient, which is 2.5. Okay? That means that it's important to compare theory with experiment, and that you should never trust some calculation, even done by Einstein. Okay, so now the second thing, so that was at the beginning of the 20th century. Now, when we move, it took a lot of time to find the second correction in volume fraction of particle when you continue to add the particle. And it took a lot of time. And it's in the 70s and the 80s that we have Batchelor, who really tried to put together the interaction, hydrodynamic interaction between the particle. And the difficulty now, instead of having one particle, you have many particles. The difficulty is that the hydrodynamic interaction between the particle is long range, meaning that it's decreasing kind of slowly. Meaning that it's very difficult to compute when you have many particles, because you end up having diverging integral. That's why it took nearly 70 years from Einstein to Batchelor, okay? And again, here. And then at that time, in the 80s, we started to have numerical simulation, in particular, the Stochasian dynamic. I will show you a movie about the Stochasian dynamic. And now we come to the 2000, and now we try to understand the dense suspension. And the big paradigm is to say that, well, now we need to understand the contact, the direct contact, because there is not only hydrodynamic, but there is direct contact between the particle. And the idea is that when you have, at some point when it's very concentrated, the particles are jamming, and you want to understand this jam state, which is an extended network of contact, and you need to understand this interaction. And the idea, which changed a little bit this paradigm, is to say, well, instead of going and say, well, I'm going to add the interaction and compute the interaction more finely or whatever, no. The idea was to, by the group of Mathieu Viard, is to look at the jam state, and then to say, well, we have weak contact, And if we cut this contact, the system will flow. And we want to understand how it is. So as you will see in the following, I will be more interested in the very dense system, but it's to give you an idea of how things are going. Okay, now, rheology of dense suspension. I will start with something the simplest possible. I suppose that I have sphere, which are non-Brownian. They are hard, they are monodisperse, and they are neutrally buoyant, meaning that in the experiment, it's simple. You have a density of the fluid, which is the same thing as the density of the particle. So now, because it's very viscous in that case, we are in a very viscous case, we have a viscous scaling of the shear stress, and the shear stress, because we don't have any inertia, everything is linear, and the shear stress is proportional to the shear rate. And you have here, you have the shear at gamma dot, and you have here eta f is the viscosity of the fluid, and here you have this relative viscosity that are already introduced, and this is depending only on the volume fraction. And this is what is plotted here on the right. In color, I collected a lot of experiments, and you can see that the viscosity is increasing with volume fraction. This is what we know even from Einstein. The only thing is that Einstein equation is here, and it's a dotted line here. So you see it's going to work below 10% volume fraction. And when you increase the volume fraction, what you will have is you have hydrodynamic interaction, and you have contact. And at some point, when you continue to increase, you can see this data here. You see that it's diverging. It's diverging at the maximum volume fraction, which is smaller than the random close packing, which is 64%. It's about 54 to 62%. It's really dense. And actually, this shear jamming fraction varies depending on the size and the distribution and surface interaction. And what I want to show you here is that you have another curve here. And this is numerical simulation, actually. We have two numerical simulations. One, which is here, the big star in black. And this is where the particles are frictional. And here, when it's the cross here, it's frictionless. And you see when it's frictionless, it's diverging basically at 64%. So this maximum volume fraction depends on the close interaction between the particles, meaning that when the particles are together, when they contact, there is some friction. And it's really important to see that and to understand that. And okay, so this is one thing. And you can see that when you look at that, well, the viscosity will be an increasing function of the volume fraction. It will diverge at the maximum volume fraction. And it's sort of quasi-Newtonian behavior of the shear stress. Now, there is particle, and they can do what they want, of course, because the suspension mixture is compressible, but the particle phase is not, okay? And if you think at the same system when you shear a suspension, actually the particles are colliding, and they have interaction, and they create a force against the wall, and this is a particle pressure, a little bit like in a gas, you know, when you think about it. And this particle pressure, which is the pressure coming from the particulate phase, is something which is also characterizing the rheology of the suspension, okay? And this is something we want to understand, and you will see how important it is. And there is this particle pressure has also viscous scaling because we are very viscous here, and you can define a viscosity, which is a normal viscosity, which is also depending on the volume fraction, and it's plotted here versus the volume fraction, and you see that it diverges also in the same way as for the shear viscosity. Okay, it's diverging the same way, but of course it's 0 when there is no volume fraction. Volume fraction 10 goes to 0, and this particle pressure is crucial from the two-phase modeling. This is what Bernard said about what we try to do, because we have two phases. We have the fluid and the particle, and as I said, the mixture itself is incompressible, but the particle phase can be compressed. Okay? So you have, and this particle pressure play a crucial role in the modeling. And I wanted to show you some example, which is really important. It's the shear-induced migration. First thing we show you how this rheology of the suspension differs for the rheology of the single fluid. And this has been observed since a while. So it was observed in the 60s by this group, by Mason, and also later by Akrivos, and there is a lot of paper on that. And when you have a flow of particle or suspension in a pipe, the particles are migrating toward the center of the pipe. And you understand that it's important to understand that, because when you carry material which are particulate, if it's migrating towards the center, at some time it can plug or do some weird thing, okay? Same thing, what happened here, it's a picture of the rheometer, which is a Couette flow. You have two cylinders, okay? You have an inner cylinder which is rotating. Inside, you put your material, this is the rheometer, and then you turn the inner cylinder, which is here. And what Akrivos and Leighton found is that they were seeing that the viscosity was decreasing, actually, just because the particles were migrating from region of high to low shear, just like in the pipe flow, but here it was near the rotating cylinder. So with time, you had your viscosity, which was changing just because the particle was migrating. So I want to show you some experiment we did with the same technique I mentioned before. It's a pipe. We have some particle of PMMA. They are neutrally buoyant. And again, we use this index match technique with some rhodamide in the fluid, which is bright, and you can see the particle inside is black, and you see that they migrate toward the center of the pipe. Okay? And I just want to show you, for fun, the first numerical simulation of that problem. I mentioned Stokesian dynamic. It's one of the first numerical simulation which can use discrete numerical simulation of particle. It's in 2D. It's an old movie. I think it's fun. And you will see that at some point the particles are migrating in the middle. And this is what you end up at the end. That was a fundamental paper which explained this thing with North and Brady paper. Okay. And just, here I have a few equations. I'm sorry for that. I wanted to give you a flavor of the two-phase modeling. And we can have two-phase modeling, and you remember I talk about this particle pressure. It can be, it's a normal stress also. It's the same thing. And basically this particle pressure, if you take this normal stress, if you take the divergence of this normal stress, you get a force, okay? You get a force which drives the particle in a pipe toward the center. And the idea is to say, well, when it's fully developed, when everybody has migrated towards the center, why it's happening? It's just because the pressure, this particle pressure across the pipe, here, should be 0. And this particle pressure is this normal viscosity, which depends on the volume fraction, multiplied by the shear rate. But what happened is that since the shear rate varies, it's very important on the side of the pipe, but 0 in the middle, the concentration must also vary. And in such a way as to keep the particle pressure constant across, okay? So when the shear rate is low, the concentration is high, and vice versa. So it's a very simple way of explaining this migration. Of course, it's a little bit more complicated than that. But, okay, so now I wanted to give you an idea of the more funny effect on suspension rheology. And the first thing is, can you walk on water? Of course you cannot. And you will see that this lady is trying to walk on water and sinking, of course. And then they did this huge pool of cornstarch in Malaysia. I think it was sponsored by some bank or something like that. And you will see that you can walk on cornstarch, okay? And you can see that. Of course, if you can walk. You have to walk fast, and then, of course, if you stop, you sink. So you have to be careful. Okay. So what's going on here? And what is shear thickening? And shear thickening, it's depicted here. You have the viscosity, and this is the shear rate. And when you increase the shear rate, at some point, the viscosity jump. You have two types of shear thickening. You have what they call the continuous shear thickening, where it's just increasing a little bit, like that, the curve here. And then you have the discontinuous shear thickening, where there's this jump here. You can see suddenly the viscosity diverge, okay? And there have been debate for ages, not for ages, but let's say since the beginning of the 20th century, to understand this thing. Unfortunately, it doesn't go so far. And people have come up with different type of theory, okay? And they all fail. So, and this happened for suspension, which are both Brownian, with colloidal, and some non-Brownian suspension. So that was really, people were wondering what's going on. Okay, and now what I just told you about the suspension of hard sphere is that there is no shear thickening in regular granular suspension. The shear rate is proportional to gamma dot, and it's shear rate independent viscosity. So there is no shear thickening if you have hard sphere, like I mentioned. So you need an additional ingredient. And the idea which came up, as you can see more in these years, by two different groups, numerical, or three different groups actually, is the idea is the following. It is to say that what happens is that the grain, there is a little repulsive force. So there is an additional force, a repulsive force, and which prevent the particle to touch. And at high shear rate, you have contact which form, and the friction come into play. This is what you see here. The particles start to touch, actually. And the key ingredient is the combination of this repulsive force and the friction. So what happened is that at the beginning you shear, but it's not very concentrated, for instance. The particle don't touch. There is lubrication in between the particle, while at high shear rate, there is contact suddenly, because the shear stress break the repulsive forces. Okay? So what happened is, I have more movie here when you see that you can walk and you can do all sorts of things. And the thing is here is that you see that I have plotted two curves for the viscosity, one in blue, which is when you have friction, and one in red when you have no friction. And actually what happened is when you break the repulsive force, you jump from the red to the blue, like that. And you can see here. Or here, you even can jump to a jamming. So that means that this transition of shear thickening is really due to a frictional transition going from lubricated contact to frictional contact. This is to tell you how friction between the particle can alter drastically the suspension rheology. Okay. And now I will, for the end, talk about sediment transport and tell you a little bit about what we're doing, and also the connection with the friction. Okay? So here, again, this is a self-compacting concrete problem, or this river of rocks. Okay? And we want to understand the rheology, and I said to you, we do something much simpler. We take a pipe, it's a square pipe, and we put some sediment, some spherical particle in it, and we try to look at them, okay, with this matching index technique that I mentioned several times. And we have this laser, which is here, illuminating the cell. And we look at this viscous regime, okay? And just to show you, this is something that I show you here. Okay, yeah. This is what I showed you before. This is the transport of the particle, the sediment transport. And what we can do is, because we have particle, but we have also this little, actually we use fingerprint powder, which are here, and we can measure both the velocity of the particle, but the velocity also of the fluid, by using what we call PIV, which is particle image velocimetry. This is somehow to do some averaging into a little interrogation region. Okay, and what you can get is typically the flow, which is developing. You can see in blue on the top, it's a kind of Poiseuille flow. And in red, it's the flow which is inside the particle. Okay? You can also use other particle. This is borosilicate. And you can see we can measure directly the flow inside the bed, but we can measure also the volume fraction. And you see that the volume fraction is not varying much, except on a little layer, a few diameter of particle on the top of the sediment here. Same thing here. here. Okay. And there is no slip nearly between the particle and the fluid phase. Okay. So this, actually, the important thing is that we had this nice experiment and we could compare it with now very powerful numerical simulation in the group of Bernard and Eckhart also maybe. And actually, this is it's direct numerical simulation where we solve completely the flow around the particle, but also the contact, the friction, the rolling of the particle, everything. And I show you a little bit a movie that Bernard gave me. And you increase the flow rate, and then you decrease it, and then you end up having a stationary bed, and you have a flow profile which we compare to the experiment. Okay, but what is interesting is that we can use the numerical simulation as an experiment. And the interesting is that we have things in the experiment that we cannot access. For instance, in an experiment, you can have the global rheology of the mixture, but you don't have what gives you the fluid or what gives you the particle. And this is what the numerical simulation is giving you. And this is what we have here. This is the shear viscosity versus the volume fraction. Here it's the total contribution of fluid and particle. And you see that it's increasing and diverging at a certain volume fraction, as I mentioned before. Now, what is interesting is that with the numerical simulation, we can separate the part which is coming from hydrodynamic and the part which is coming from the direct contact between the particle. And you can see that the contact at the beginning between the particle when it's very dilute is not important. And hydrodynamic is very important, it's in blue. And then at some point when you hit about 40%, you can see that the contacts are dominant. And in the bed, the hydrodynamic is not doing much. And actually, it's very close to the Einstein relation. And why is that? It seems surprising for the sediment transport. It's just because the particles are touching, there is no hydrodynamic interaction between the particle. You know what Bachelor found, like this contribution in phi square. It's just the first term, because the calculation of Einstein is just that you put one particle in a fluid and look what it gives you. And because basically the hydrodynamic interaction has screen. And that was a really important result to show that in the sediment transport, it's a little bit different from what you get from the rheometer. Okay? And, okay. So now, it's close to the end of the talk, and I think the important point in the change in paradigm is to say that while hydrodynamic interaction is important in the dilute regime, they become of lesser significance in the dense regime, and contact prevail, and the friction between the particles prevail. And that was something very important, and you see that this shear thickening, for instance, and the fact that it's a transition between lubricated contact and frictional contact was a very important idea to understand what's going on. It may not explain everything, but at least it gives some idea. Of course, we have more open problem with non-spherical particle, because I spoke about sphere, you know. In hydrodynamic, everybody's starting with a sphere first. But you have fiber, you have platelet. For instance, if you have sediment transport in a river, sometimes it's platelet, little plate. And it's very important to understand that. You have also the colloidal interaction and the nonlinear rheology. I already spoke about shear thickening, but there's also shear thinning, another problem. You have non-Newtonian fluid. You have deformable particle. This is, for instance, red blood cell. And you have polydispersed active particle. There's a lot of people working on the rheology of, for instance, bacteria. And you have suspension and interface. And then there is inertial suspension. And I will talk a little bit about that, because all that I mentioned here, everything was very dense, everything was very viscous. And now, what's going on, if you think about, for instance, the avalanches, there's a river of rocks, it's not only viscous, there's also some inertia. And maybe we are even in a transitional regime between viscous and inertial. And when you think about avalanches, and for instance, what happened recently in Switzerland, you have a regime which is probably, it's very dense, but at the same time, I'm sure it's inertial also. So it was important to understand what is the transition. And this is something we did with Franco Tapia, who is here. It's looking at the viscous inertial transition. And you remember I told you that when it's very viscous, the stress is scaling linearly with the shear rate. But there is another scaling when it's inertial, and that was Bagnall, also a great name of granular flow, who described that in 1954, that the inertial stress scale is going like gamma dot square. It's just here, I'm not giving equation, it's just scaling, linear dimensional analysis, okay? And here, it's some experiment we did with very big particle. You see they have nearly 5 millimeter, it's PMMA, in a rheometer, which is a little bit special. I won't give all the detail, but the idea is that this is the shear viscosity, this is the normal viscosity that I introduced, and versus the Stokes number. And the Stokes number is just the ratio between the inertial and the viscous stress scale, and it's going like gamma dot. And you can see that here, you have different viscosity, it's a color, and different volume fraction. This is a different symbol. And at the beginning, if Stokes is small, you see that the curves are flat. It's just because we are in the viscous regime, in this Newtonian regime, everything is linear. Like the viscous, the stress is scaling like gamma dot. Okay? Now, at some point, when the Stokes is around 10, it starts to increase, and then you see it's going linearly like gamma dot, meaning that the stress is scaling like gamma dot square, meaning that we have hit the inertial regime. So here, we're going from the viscous regime to the inertial regime. And what we found is that there is two different scaling of the stress, okay? And even more than that, if you want to connect with the first graph where you have this increase in viscosity like that for the shear stress and the particle pressure, you can find the same thing if you normalize this shear stress and particle pressure by the addition of the stress scale, meaning the viscous stress scale plus the inertial stress scale. It's a surprising result, because why it will be just a simple addition, I have no idea. It's like that. And then we want to understand that. Why do we have this change from the viscous to the inertial regime? And this is what we're trying to understand now. And we're using now numerical simulation, which mimic a little bit of experiment. And I can show you what we discovered very recently is that in the viscous regime, actually, the contact between the particle, and you can see them here, you see that the particles are rolling against each other in a kind of chaotic manner, and they exert a very high pressure on the top plate, while in the inertial regime, they just slide against each other, and you don't have so much on the top plate. And this is what we're trying to understand right now in the group of Bernard here in Dresden with Sudarshan, who is here, who made this nice movie. And this is really what we're trying to understand. And of course, this is a little bit fundamental as a research, but I think if we have this scaling, just by using this scaling, we can use this constitutive law, and then we can apply that to really practical problems like the avalanches, the debris flow, and things like that. And there are people at the Institut Physique du Globe who are already using what we're doing. This addition of the stress scale that I'm mentioning, it's Anna Mangenet, who is, and they really try to use that, and they can compute the avalanches on very complex geometry using this kind of ideas, and this can help protecting or some, like we've seen in Switzerland, the village has been completely destroyed. And this kind of event, clearly, which are rare, they're going to be more frequent in the future because of climate change and maybe more intense. So I think it's important to understand the rheology of suspension. I hope I tried to convince you about that. Thank you very much.
Yeah, thank you very much for this really very nice talk with wonderful movies and so and some exciting formulas. And so the paper is now open for discussion.
Yes.
Yeah.
Yes, you mentioned the suspension viscosity, and you said there is there is friction or there is no friction. Yeah, in this graph you had.
Yeah, you can have two curves.
Yes.
One for when there is friction with the particle, and one where there is no friction. Yeah.
Yes, but I could have different surface roughnesses.
Yeah.
And play with the friction coefficient, for example.
Yeah, I think it's really the friction coefficient which matter.
Yeah,
It's,
so
the roughness can be linked to that, but it's really the friction coefficient between the particle which matters.
has it ever been tried to coat the particles by some other materials to play with the roughness and the friction coefficient?
So what we did with Franco, actually, we did it's very difficult experimentally, what I mean. Numerically, actually, what...
I have a number, of course.
Numerically, actually, Sundarsan is trying to run numerical simulation with particle without friction. In experiment, it's very difficult to have particle without friction. Extremely difficult. And so what we did the opposite. We increased the roughness, and so we increase a little bit the...
and you have some intermediate curve.
Yeah.
Okay,
but to decrease, actually, if you have capsule, for instance, you can have, there's some people who have used capsule, but they are a little bit deformable. That's another problem. And to have particle without friction, and we use also some hydrogel. But there is also the deformability, which comes into play. It's another problem. Okay, thank you.
Thank you for an amazing talk. I had a question on the particle migration. Why would particles near the wall not move as much?
I think, In the numerical simulation and in the experiment, they both stay. Yeah. I think they get stuck there for probably the interaction with the wall, you know. It's really strange, but yeah. Even in the numerical simulation, you have some particles which are maintained on the wall. I think it's there's some, maybe they get stuck there, there's some interaction in the experiment, I don't know.
Okay, yeah, thank you.
So I'm not from that area, but I would like to know how do the particles know that they need to move that way, and and why do they choose the way? Like, why do they get pressed together? Because they don't have. It does not have any brain or something like that. How does it know?
No, they don't have.
Do you know?
They have a mind of their own, but not brain, probably. Yeah. You mean for the migration, for instance?
Yeah, not only that, but I mean also how do they know that they need to turn that way? Because you examine that, but from where does the information come for the particles?
Well, really, it's coming from the mechanics. It's not for the brain of the particle. For instance, for the migration, it's really, you need to think of this particle pressure like in a gas. Mm-hmm. When you compress something, the particles are going to compress and move, and they are compressible. What we try to understand right now is what happens when you are viscous and when you are inertial. And you've seen when you are viscous, there's a lot of rolling, and while when you are inertial, there's a lot of sliding because, and it's a little bit counterintuitive because you will think that somehow when it's viscous, you have a lot of lubrication and they may slide. But no, actually, they roll against each other like that in the viscous case. But this is something which is not understood fully, and what we are in the process of trying to understand.
Thank you.
Earlier on, when you gave you said simplified explanation of why these particles would clump up in the middle, you said something along the lines of that the particle pressure stays constant or something. I'm not sure exactly what statement.
It's the divergence of the norm. Basically, what you write when it's fully developed. You write that the divergence of the normal stress of the particle phase is zero. And actually, in 2D, it's simply that the pressure across the, not the direction of the flow, but the direction of the shear is constant.
Okay.
And meaning that and then since the particle pressure is the normal viscosity, which depends on the volume fraction multiplied by the shear rate, since the shear rate is varying, it's very strong near the wall of the pipe and zero in the middle. You have to have the normal viscosity to vary, and the only way to do that is vary the concentration. That's why there's this particle in the middle.
Okay.
But really, the motto of that, what's driving this flux toward the center is the fact that you have this particle pressure, which is on normal stress. And the divergence of the normal stress is giving you a force, which drives the particle toward the middle. And really, the majority of the important thing is really that it's due to the contact between the particle and the bump between the particle, like in a gas. And this bump is creating a force which is driving the particle towards the center. I hope, if it's clear.
Yeah, I heard, but I don't understand very well because I'm also not from this field at all. I'm, in fact, from no field. I'm just a student. So the divergence staying constant just is the fact because the scenario is fully developed, so no more changes happen.
Yeah, but now
Okay.
you can have also a transient, and we can. I didn't want to show you that because it becomes very involved and very complicated. But you can write a migration equation.
Okay. Another question. Considering the importance of understanding granular suspension flows and that computation resources might be limited at a university, has your team considered to start like a distributed computing project for your simulation tasks, something similar to folding at home, which I don't think it runs anymore, but it used to let participants donate their own computing power to calculate protein folding tasks.
Mm-hmm. Do you think?
No. Has your team considered doing that to, so to speak, extend your computational resources?
I'm not doing the numerical simulations, Bernard, but they have big computer, I think. Huh?
I guess we're running most of our simulations here at ZIH, and there are initiatives to go to hybrid hardware solutions. We are not directly involved in that yet, but it could be a potential for the future. But right now, I think TU Dresden is doing a very good job. I'm very happy to say that the computing facilities are very nice and facilitates a lot of the simulation work we can do and we want to do. Yeah.
And I think what is important is to combine simulation and experiment and modeling, actually. We have this two-phase modeling, we have the experiment, and we have the direct numerical simulation. By combining these three things, maybe we can achieve something. We'll see.
I think, oh yeah, sure.
More questions. Good.
Sure. As far as I know, sediment, when it moves in water, at least, tends to erode over time. Would your team also study such like erosion processes and their influence on the entire movement of grains?
Mm-hmm. Well, we start with sediment in bed, and then we have a flow, which is a kind of Poiseuille flow, and we look at the erosion. And we also look at the starting of the erosion process, which is, you describe the Schill number, so it can be described as some number, like that, yeah.
Okay, cool, I think that's it.
Yeah, thank you very much for the, yeah, there is one, yeah,
another
Peter.
question.
It's going to be a completely different question. Suspensions, in reality, they are very seldomly made from spheres. And I have a very special case in my field of research, and this is bioreactors. Mm-hmm. So what we find in there is a very high concentration of microorganisms, billions of microorganisms in a few cubic meters, and they form flocks. So there is a huge enclosure of water within flocks. Yeah. So the density of the material of the higher density flow, if you think about the two-phase flow, is not that much higher because the volumetric fraction is taken by enclosure of water, basically. Okay. So they are not really very stable
so you have
particles.
Flocks?
The flocks are touching each other.
Okay.
And now going back into the past, more than 30 years ago, I tried to model flow in such suspensions by using turbulence models. Was that completely wrong? Should I have applied
I have to look.
laminar models in order to represent the viscous flow?
They were using the rheology of viscous flow, or what they use?
No, I was working with the K-epsilon model at that time.
Yeah. So I don't know. I have to look carefully. Maybe we can discuss.
Okay.
That.
And the second question would be, could you think about transforming your findings with the spheres suspensions into such a more complex world?
Well, actually, we already did some experiment, for instance, and I think it's more complicated numerically, but with, for instance, fibers. And actually, for sphere, the divergence, which is going like that, it's diverging like -2 with the distance to jamming. And for instance, with fiber, it's diverging with a power of -1. But still, we don't know why. And clearly, all this rheology is due also to the network of contact. And we understand that for a sphere or for a fiber, the contact between the particle will differ. So I think it's linked to that. But we don't have a complete understanding yet of all that, really. But I think this is the idea, and the idea to go to, I think Sunderson would like to look at elongated object, I think. Yeah. Thank you.
Other questions? If not, I have the final question. So,
good.
So if we understand all these things better, and you said that in the future we have to face more of these accidents like we saw in Switzerland now, how would this help to maybe predict what is going on, or to even help to change the way these
well, I guess you will not predict, will be maybe difficult, because...
predict the flow? Or?
Predict the flow, for sure. Mm-hmm. That's the idea. If you have a sort of complex geometry in mountain or whatever, we can predict probably the flow of the sediment which is falling, and at least tell if a village needs to be evacuated or not. At least, I hope that we could achieve that, at least.
Good. Yeah, so thank you very much for the presentation and the audience for the discussion. I think it was an exciting evening, and hope you will be successful together, and we will read much more wonderful publications from you. Thank you very much. Good night.
Thank you. Thank you to you. Oh, thank you. That's very, very nice. I hope you. Thank you.
Hope you enjoy it.
Thank you. Thank you very much.